Hello everyone. In this video, we will introduce a new tool called comparison test, using which sometimes we can show an improper integral is convergent or divergent without computing that integral itself. Okay, so where this idea comes from. So consider two functions, both positive, say f and g. So red is g, blue is f, and we know that on the interval from a to plus infinity, everywhere g is bigger than f. Then you look at the area under the graph of f. Okay. This graph, since it goes up to plus infinity, it's an improper integral given by improper integral. If this improper integral is divergent, so in other words, the area under the graph of this function is not a finite number, then definitely the area under the graph of g is going to be infinite, because that area is always less than the area of the region under the graph of f, yes? So if the area of the smaller one is infinity, then the other one is going to be infinity. So in other words, if integral from a to infinity of f of x is divergent, then the integral of gx from a to infinity is going to be divergent as well. On the other hand, if the area under the graph of g, which is the bigger area, is a finite number, the area of the smaller one must be finite, because that area is smaller than the area under the graph of gx. So this is the comparison test. So let me write it here. So we have two continuous functions. So let f and g be continuous functions on the interval a to plus infinity, and we know that for all x's, which x is bigger than equal to a, f of x is less than or equal to gx, and f is always positive. So we are dealing with two continuous functions, one bigger than other one, and both of them positive. Then there are two cases. If the integral of the smaller one from a to infinity is divergent, there is no other way that g can have convergent inverse. So if the smaller one is divergent, it will push the integral of the bigger one to go to infinity or to be divergent as well. Or the equivalent version is that if the bigger one has a convergent, so here bigger one is gx, convergent integral, then it will force the smaller one to have convergent integral. So this way, if you find a function which is easier to integrate and it's bigger than the given function, and that bigger function is convergent, you can conclude that the smaller function will be convergent. Okay, let's see this in some examples, specifically this example here. This function here, e to the power negative x squared, it's called Gaussian, so it's very famous function. And even more famous thing about it is that you cannot find an antiderivative for this function and express it using basic functions that we know, using sine, cosine, trig functions, rational, all this. There is no such function. In other words, computing this antiderivative is just off the table, and you cannot evaluate this function using fundamental theorem of calculus and then definition of the improper integral. So what should we do then? We are going to compare this to another function that can be integrated, and then using comparison theorem we will show that this integral is convergent. Okay, so how do we compare? So I want to start with the point that x, we are only working with x is bigger than 1, yes? There is that x squared in the power of e, so I will multiply both sides by x. This will give me x squared is going to be bigger than or equal to x. There's minus sign there, I multiply that, but that changes the direction of the inequality. Then we know that e, the function, the exponential function, is increasing. So that means that if number one is bigger than the other one, then e to the power those ones will keep the inequality as it is. And well, this is what we are looking for. This is my function. This is a new function, and I know that both of these guys are going to be positive functions. So in other words, our function here is the smaller function, and we found a bigger function. That is where, when you're trying to prove that your function is continuous. Now, if I show that the bigger function, when you want to show that your function, the integral of your function is convergent. Now, if I can show that the bigger function has a convergent integral, then we are done by the comparison integral. So let's then focus on our function, the upper function that we just found, and try to see if we can evaluate this. Well, why this is a good upper function? Well, simply because I can evaluate this integral. This is negative e to the power negative x, go from 1 to t, and then I will find the limit. This is minus, okay, limit. Negative e to the power negative t plus e to the power negative 1. But as t goes to plus infinity, you can look at the graph of e to the power minus t. This will go to 0, so this will be plus 0 plus 1 e to the power negative 1, or just 1 over e, yes? So what we showed is that the integral, so f of x, which was e to the power negative x squared, was less than g of x, which was e to the power negative x. That's the first part. And we showed that the limit of the upper one from 1 to infinity is convergent. Okay? Then as a result of comparison test, the smaller one, which is what we are started to look for, has a convergent integral. Can I say anything about the limit or the value of that? Comparison test has nothing to do with the limit or with the value of the improper integral. The only thing that it can tell me is that the integral of the smaller one is going to be less than or equal to value of the integral of the bigger one, which is 1 over e. That's the best thing it can tell me. Okay, so we've proved that that integral is convergent. Let's do another example. Here I have 1 plus sine squared x over x. I'm going from 3 to plus infinity. One thing to note, that if there was no x there, that this was an easy integral to evaluate, but now with x there, we are in trouble. It's not going to be an easy thing to do. Well, let's start then working on our function sine squared x over x. Okay, so this is my function. Now we are working on x is bigger than 3. Okay, now remember this sine x is between -1 and 1, but when we square it, it's going to be always bigger than 0 and less than 1, yes? Then from there, if you add 1 to all three sides, this will give me this value, yes? And then if you divide all sides by x, now I found my function is less than 2 over x and it's bigger than 1 over x. Which one I should use? Okay, so the part, if you wanted to use the upper one, like this one, you have to make sure that the new function you found has a convergent integral, so that I can use comparison. But if you're using the lower one, you have to make sure that the lower one has divergent, and then you can use comparison test. Here, both of them are multiple of each other. So let's just consider 1 over x, which is the half of 2 over x, yes? So the convergence and divergence of both of them are going to be the same. Here, you remember that p integrals, p equal to 1. If p is anything bigger than 1, then that is convergent. Now it is not bigger than 1. That means that this is going to be divergent integral. Since it is divergent, so then we must take the one which is less than our integral, so that we can apply the comparison test and push that upper one to infinity. So this is going to be my lower integral, lower function, and that is going to be upper function. And you can ignore this other side of this inequalities actually. Okay, so this way now I found that the smaller one is divergent, and well, it's already shown that 1 over x on the interval of the integration is less than our function. So the comparison test tells me that the upper one, integral of the upper one, which is what we have there, is going to be divergent. And that is an interesting fact, because we didn't integrate 1 plus sine square over x, which is not easy integral to evaluate, but we now can say definitely this integral is divergent. So comparison test, you have to be able to apply it correctly, and also you have to see that only very specific form of that works. So if the integral of the lower one is divergent, then the upper one is going to be divergent. If integral of the upper one is convergent, then the integral of lower one is going to be